Hello, my name is Chris, and I am making this video under the assumption that your Calc 2 professor sucks at their job. Maybe they don't. Maybe you're a terrible student, but I don't really care. My goal here is to show you basically how to parameterize some stuff. I don't know if I'm going to do more than one example in this video. You'll know because you will know because you will have read the title. But I do not know yet. But we're going to start out with a problem that is find an equation for a plane which contains some given points. So let's write down our given points here. These are example points, obviously. So make sure you check your problem and you're not just like auto copying this, you know what I mean? Going on autopilot. So these are my 3 points. I got 1, 1, 2, 2, 0, 1, and 1, 2, 1. So you want to designate one of these points to be your initial point. I'm going to choose this one. Sometimes you'll have a nice one. If you have 0, 0, 0 as one of your points, I would 100% recommend choosing that as your initial because you're going to need to do final minus initial, right? This is just something that is convention in physics and math, final minus initial. But if your initial is 0, 0, 0, then you don't really have to do anything to your final. You can just copy it over. So we're going to do 2, 0, 1 as such for P1, and we'll call this P2. So 1, 2, 1. All right, awesome. Now we're going to subtract our final, or our initial point. Sorry, these are our final, 1, 2. And we'll have initial, which will be the same point for both. I'm going to write this in a really dumb way. Don't do this if you're trying not to introduce error to your equations. All right, so now 2 minus 1, well, what is 2 minus 1? We have 1, comma, negative 1, comma, negative 1. So now we have our direction vectors. If you hear your professor saying direction vector in class, this is what they're referring to. All right, these are our direction vectors. Let's do a smiley face on there. All right, so you're gonna take the cross product of these two vectors. I'll explain the rationale after the main explanation bit. I just don't wanna bore the people who are just looking to grind through this problem, right? So we're gonna take the cross product of these. I like to do the IJK method. I think it's just very easy to introduce error otherwise, and you can simply just not introduce error. So for our I component, J component, and K component, well, what is our I going to be? We're going to cover this row, right? And we're going to cover that row. It doesn't vary. There we go. So negative 1, we're going to cross them, right? Negative 1 times negative 1 is going to be 1 minus, inside the parentheses is always a minus. So negative 1 times negative 1 is 1 minus 1 minus negative 1, which is 1 plus 1 for 2. All right, let's look at our J component. Here we go. 1 cross 1 is negative 1, but remember, on the J component only, we're going to do negative because that formula ends up being I minus J plus K. So negative 1. Sorry, let me do some quick mental. Oh, it's just 0. Okay, so our J is just going to be negative 1, but it's negative negative 1, which means it's just 1. Cool. And then for our K component, let's do the same thing. 1, 1, so 1 minus, and then this will be 0, so this will just be another 1. Does that seem right? That seems right. All right, so now we have our cross vector, which we will call, we won't call it anything, but we're going to do 2, 1, 1, like that. All right, so now you have your 3 points. You're going to take the direction vectors, right? Final minus initial, make sure your initial point is always the same point. And then you're going to get 2 direction vectors, which you're going to then cross with each other to get 2, 1, 1 in my case, but this will be your normal vector. So this vector is normal to your plane, meaning it's orthogonal or 90 degrees to it. Again, I'll do an explanation at the end of the video. Now, here's kind of the tricky part, but not really. This is actually kind of the fun part. You're going to put down an x minus, you're going to take your first initial point value, in my case 1, x1, and you're going to turn this into a vector, and you'll see why in just a second. But x1, and then you're going to get y minus, in my case 1 again. Again, we're taking from this initial point, right? Z, make that clearly a z, minus 2. All right. Now we're going to dot product this, with our normal vector, which is 2, 1, 1. Now that we've done that, dot product is pretty easy, right? It's going to be 2x minus 2
plus y minus 1 plus z minus 2. Make that very clearly as z once again. Equals 0. Now we're going to move all of our real number, our non-variable numbers, our constants, over to this side. So that's going to be 1, 2, and then it looks like another 2, and I think that's all the constants. So this should be 4. Unless, oh no, I'm missing a 1 here. So this should actually be 5. All right. And that's going to be 2x plus y plus z equals 5. And that is the equation for a plane. So let me go ahead and box that in as such. That's going to be our equation for the plane. Now I want to explain the rationale as to why we take this cross product, and then I'll kind of explain the rationale behind the dot product as well. But basically, if you have a plane, right, let's put down a little coordinate system here. Maybe let's draw it a little better so it doesn't look like a 5-year-old made it. Let's put it, there we go, right through the center there. All right, now let's say you have a plane that lies in, we're going to call this my x, y, and z, so you can kind of imagine x and y from Calc 1, right? We're just looking at like a flat plane, and then we now have our z element. I have 3 points that define this plane, and obviously this is not like a one-to-one translation. So now we have 3 points, and this is why that initial point was so important, because by keeping that initial point consistent, now we have a point that is shared by both of these lines. That's pretty cool, right? Now that means that these lines also lay completely within your plane. So now what we do is we take that cross product, and this is kind of the cool part about it. When you take a cross product, I'm sure you've learned this in class, but what you're essentially doing is you're taking 2 vectors, so we'll call this vector A and then vector B, all right? So B, A. Now, you're going to take these 2 vectors, and doing a cross product shows you a vector that is perpendicular to both of them. So you'll see that's a 90-degree angle, and then if we look from this side, as such, that's also a 90-degree angle right there. And that's what the cross product does, which allows you to make a line that comes out of your plane like this, or like this, depending on how you do your cross product. So now you have this line that comes completely 90 degrees out of your plane. So now we're going to take our dot product. The dot product's kind of the trippy part of this whole process, but essentially you're going to just set an arbitrary point x, y, z that lives somewhere on your plane, x, y, z minus our initial. So it's the same process we're doing up here, right? Some point minus our initial point, some point minus our initial point, but this time it's not a real point. So I drew it by signifying this little open circle here. But remember, by doing final minus initial here, we were able to build vectors. And by doing our arbitrary point minus our initial point, that shared point, it's going to draw a vector right here. And then we're going to take the dot product with our normal. And I'm going to show you why that's so important. So a dot product, if you remember, signifies the tiltiness or the alignment of a line. So this will produce a dot product of 0, and this will produce some real constant dot product. So if we have a dot product and we set it equal to 0, we are essentially forcing the angle that these 2 vectors create to be 90 degrees. So now what we can say is, well, we have a normal vector that is 90 degrees to our plane, so it's coming out of our plane, and then we're setting something that's forced to be 90 degrees to it. So let's say you have vector A coming towards you out of the page, and then you have vector B, right? If they're both aligned, it's going to produce some large dot product. But if they're 90 degrees to each other like this, it's going to always produce a dot product of 0. Now it can be 90 degrees like this, or like this. Imagine if you had a line here, and you had, I don't know, a point coming out here, and 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 you know, so many lines to the point where it essentially forms a disk. But all of these lines are still 90 degrees to this line, right? So now you have your normal vector and your arbitrary vector, and you've dotted them to force them to be 0. Now that's why it doesn't matter where you put this arbitrary point. This x, y, z could be on the right side of the graph or on the bottom half of the graph. It doesn't really matter. The point is, if you were to make a point arbitrarily that lives somewhere on this plane, it's always going to have a 90-degree angle to the normal as long as you get that dot product to equal 0. You can kind of think about this like a true or false statement. So the equation of your plane must have a dot product such that your arbitrary vector and your normal vector produce a dot product of 0. And that true or false condition being satisfied allows you to construct the equation of the plane. This took a really long time. A like would be greatly appreciated if you would be so kind. I hope this helped. Don't feel down on yourself if this is hard. Parameterization in Calc 3 in general is very, very hard. And the fact that you're in Calc 3 is pretty impressive. So don't feel down on yourself. I do plan to make more videos like this in the future, so stay tuned, hopefully, and until next time, stay safe and stay warm.